Coverage probability is the probability that the interval surrounding the unknown parameter depends on the unknown parameter value. One of the reasons why the coverage probability and size is important is to help us optimize expected length of intervals and to help us even find the shortest pivotal interval. And even coming back and involving the Newman-Pearson limit, which is also another video that we talked about earlier in chapter 8. So it's all kind of connected and builds upon each other. Now on to our theorem. So let's talk about theorem 9.3.2, which deals with size and coverage probabilities. So we're going to let f of x be a unimodal PDF. If the interval from a to b satisfies these three following things, then that means the interval from a to b is the shortest among all the intervals that satisfy our f of x. So if the integral from a to b of f of x is equal to 1 minus alpha, has to satisfy that. Also needs to satisfy that f of a is going to equal f of b, which is going to be greater than 0. And the third thing that it needs to satisfy is that a is going to be greater than or equal to x, which is less than or equal to b. And for this, we need to keep in mind that the x is a mode of f of x. Then again, if these three things are satisfied, then our interval from a to b is the shortest among all of the intervals. So this is just the theorem for it. Let's actually see it in action. Let's see an example of it. By the way, if you wanted to see the theorem proven, it is proven in the Statistical Inference textbook by Casella and Bergen on page 442. Now, before I get to the example, I actually found part of this example earlier on in chapter 9 in the textbook. And that's kind of how I was able to get and skip some of the steps of proving and use the theorem. Without further ado, let us use the theorem to find our shortest interval of this example. So this is the example of the theorem being used and the theorem 9.3.2 being used. So let's let x1 be to x9 be an IID with a PDF of this. Then y is going to be the minimum of x1 all the way to xn is sufficient for mu that has a PDF of this. Also, we're going to let t equal y minus mu, and this is our pivot that's also, it's our PDF. Thus, we get this. So just like the theorem said, we want to take the integral. I know my a in this case, my interval is going to be 0, and it's going to be till b. Now I'm going to put my f of t here, which in this case is my PDF right here. And this needs to equal 1 minus my alpha. So when I take the integral on this side, because the exponent, it's going to look like this. And this is from 0 to b. And on this right side of my equation, I still have the 1 minus alpha because I didn't do anything with it. I plug in b for my t, and then I get this. Those two negatives make a positive. These ends right here make a 1. These ends right here make a -1. So in this case, if I rearrange it so I have the positive in the front, I have this so far. And again, on this one side, I still have 1 minus alpha. I want to try to solve to get b by itself. Since I see there's the 1, I obviously want to move it over. Since it's a positive, I subtract 1. It cancels on the left, and it also in this case cancels on the right. I have the negative, so I can divide by a -1 or multiply by the -1, and it cancels the negatives. Then I still see the b is up there with my x in my exponent, and I want to get the b by itself. So since I have e, I'm just going to take the natural log of both sides. So then I have the natural log of alpha. I want my b by itself, so I'm just going to divide by -n. Finally, I have the b by itself. And I could either put it separate like this in the fraction in the front, or I could just divide it all by -n. Doesn't matter. So that's what the b is. In the theorem and stuff, it said on the interval from a to b, since my a was 0, my interval would be b, and this is my b. Thus right here, this would be my shortest interval from the theorem, using the theorem 9.3.2.